Hello. Testing. Testing. Okay, you can leave it.
Oh yeah, license.
All right, are we good? Alrighty, so the first problem we'll be solving is a KVL problem. In the exam, normally you won't be given these arrows here. You can decide which direction you want to make the arrow. But basically, the point of the arrow determines the direction of your positive and your negative components. So this way, for this question, we have it clockwise. So we'll be going this way, then this way, and then we're going down and to the left. All right, so for the first part, we'll be solving for, we'll be doing the bottom left loop, and we have A, B, C, and V1. So we have three components that we have the values of, but we don't have V1. So basically what we will do is we enter through the negative, so it'll be negative 140 minus 150 plus 40, and then plus V1 equals 0. Um, and then we would get negative 250 plus V1 equals 0. Then we can move this to the left side by adding 250 on both sides. And then V1 equals 250. Alrighty, and then we will solve for the next loop. We'll look for where we're only missing one component. So here, solving for this one would be best if we do it last because we don't have the two of the components are unknown, V2 and V3. So we'll do the second. The second one will be the top one. So we have C plus D. Hold on, let me just zoom out. We're going to enter through, oh, sorry, it's negative C, sorry. And then we're going to go, oh, sorry, negative C plus D, and then it will be minus, ooh, that's an erase plan. Okay, so we have plus D minus V2. V2 equals 0. We have negative 40 plus 12 minus, oops, sorry, minus V2 equals 0. That will give you 40 plus 12. Oh, negative 40, sorry. Oops. We get negative 28 minus V2 equals 0. We can move V2 to the right. And then we get negative 28. Then we get negative 28 equals V2. Now we'll solve for the bottom loop, and the direction is going to be this way. Then we're going to go up to the right, and then we're going to go down. So we'll have negative V1 plus V2, and then plus V3 equals 0. And then V1 we got 250 plus negative 28 plus V3 equals 0. And we can just do that 250 minus 28. Yeah, 2 equal, oh, not plus, equals plus V3 equals 0. And then we can just minus 2 minus 2 on both sides. And then the V3 equals negative 222. All right. Now we'll be doing a KCL problem. For a KCL, basically the main thumb of rule is whatever is leaving a node. So here we have, oh, is there an undo button? There is. Okay. So whatever is leaving the node will equal whatever is coming out of a node. So we have our nodes drawn already for us. On your exam, you probably won't have your nodes drawn for you. So you will have to figure out where the nodes are located. All right, so we'll start with this node right here. Okay, so we have C equals, okay, so we have 8 plus B is also leaving, so 19 plus I2 equals 0 because they're all leaving, so there's nothing entering this node. So we just do 8 plus 19. We get 27 plus I2 equals 0. We can move the 27 to the right side, so we get negative 27. So I2 equals negative 27. The next node we can solve for is this one right here because we have I2, we have A, but we don't have I1. So we'll solve for I1 next. All right, so we have I2 entering the node, we have I1 entering the node, and we have A leaving the node. So this will be negative 27 plus I1 equals 7. So we can do plus 27 on both sides. And then we get I1 equals 34 amps. Make sure to include your units when you're doing this. All right. So we have I1, we have I2. We can now solve for, let's work on this node next. So we have D leaving, we have I4 leaving, and we have A entering. So we have 7 equals 12 plus I4. We can minus 12, we can minus 12. 7 minus 12, negative 5 equals I4. All right, and then our final node is just this one. Uh, we have I4, we don't have I3, and we have B. So B and I4 are entering the node, and then I3 is leaving the node. So we'll get, let me include my amps, sorry. We have 19 plus I4 equals I3. And then I19 minus 5 equals I3. 19 minus 5 is 14 equals I3. And we conclude our amps. That's how you do KVL. Next, I will pass it to Josephine.
All right, so the next one is branches and nodes. Not too terribly difficult. So just to review, a node is just a point of connection between two or more branches or elements. A branch is a single element. It can be a resistor, a capacitor, a voltage source, like just a single thing. And a loop is any closed path. So for this example, we just want to find the number of nodes and the number of branches. So first let's count the number of branches we have. We have one over here. We have this one, 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 this So in total, we have 6 branches. Then finally, we can go ahead and count the number of nodes, but there's also another way we can do this. If you remember the equation, the number of branches is nodes plus loops minus 1. So we know we have 6 branches. We need to find the number of nodes. As for loops, we just have 3 closed loops. 1, 2, 3. So if we solve for the nodes, that's n plus 2, we are going to have 4 nodes in the circuit. So this is a good equation to remember, just to make stuff easier. Now we're going to move on to power. So the first thing you need to know with power, it's just voltage times current. So just remember that as we go through this. So first we want to find what is the, oh, my bad. Yeah, one second. Yeah, we first want to find out what VO is. So with VO, we have this resistor, we have the current. So remember V equals IR, that's Ohm's law. So we have 5 milliamps times 10 kilo ohms. That will give us 50 volts. So with the problem, they want to first find what is the current across the 26 kilo ohms. So now that we found VO, we can find out what this is. And that's a current source. So 0.01 times VO will give us 5 amps. And there's 2 different ways you can go on from here. If you're comfortable with current division, you can go ahead with that. Or you can just try to combine the resistors in parallel, then go across. So if you go with current division, there'll be the 5 kilo ohms divided by the 5 plus 26 kilo ohms times the current that is going across it. So that'll be 5 amps. That will give you 0.081 amps. So we found the current. Now we want to find what is the voltage across the 26 kiloamps. So that again, we have the current, that's 0.081 amps. And we have the resistance, 26 kilo ohms. That will give you 2.097 kilovolts. Finally, we want to find the power. So that we just plug in the voltage and the current we found. So 2.097 times 0.081 amps. That should give you 0.169 kilovolts. So just be sure to remember either how to do current division, or if you want to go another way, combine these 2 resistors in parallel, find the voltage, because you can multiply this current by whatever is 5 in parallel with 26. That will give you the voltage. And the voltage is same across parallel resistors. So you can use that and find the current and the voltage for the 26 ohms. Or you can use this equation for current division. All right, next up is voltage division.
Great. So this problem is asking us to find the voltage drop across R1. So, okay, the way we can recognize that it's a voltage division problem is if we have multiple resistors in series, which we do right over here. So, okay, so, all right, so we need to find the voltage drop across this. And the general formula for a voltage divider is, so let's say we want to find the voltage drop across R1. We have our supplied voltage source. This will be our equivalent resistance on the bottom, aka R1 plus R2. And then this resistance value will be the value of the resistor that we want to find, which is R1. So now we just have to plug in value. That's 12. And this is 150 plus 200. And then once again, divide by 150. And we should get E value of 5.14 volts. So this is the voltage across resistor 1.
This is more of just a concept than a problem, but you may see multiple choice questions that asks you, like in an inductor, what happens? Does the current lead the voltage, or like what exactly happens? So I like to remember this. You might have heard of it, Eli the Iceman. So with an inductor, that's the L, your voltage, that's for E, that leads your current. So for an inductor, the voltage leads current. And for a capacitor, your current leads the voltage. And then when it's just a resistor, so if it's just a resistor, both voltage and current are in phase with each other. Yeah, so just remember this. It shouldn't be too big of a problem, just more like multiple choice questions over this. Eli the Iceman. Yeah, just remember how that works. So our next one up, it's sinusoids and phasors. That'll be a big part of the test. You'll see it across many problems. So be sure you got this down. Do some practice problems over this. But a few things to keep in mind. If you're doing like phases where you might get frequencies, stuff like that, you want to keep everything at cosine. It's a good way to keep stuff in track. So if you see something which is maybe in sine, you can subtract by 90, and that will get you to cosine. You would subtract the angle by 90, and you will see it in a problem we will do. If you're adding or subtracting, you need to use this format, the a plus bi or x plus yj, and then you would combine the real and imaginary parts. If you're multiplying or dividing, it needs to be in this format. You have the magnitude, you have the angle, and it's pretty easy. If you're dividing, you divide the real part as normal. For the angles, you just subtract. If you're multiplying, you multiply the real as normal, and then you add the angles. Yeah, that's for multiplying and dividing. So here we got an example of a problem you might see often. So the first thing we notice, we have a sine here. We want to convert it to cosine. So we can do it by taking the angle. Our angle is 30 degrees, and then we subtract 90. And then since we have the same frequency for both of these, the frequency is 20, we have the same for both of them. We can go ahead and convert them both to phasors. So for the first one, that's 110 minus 9, oh, sorry, my bad, minus 60 degrees. Then you have 210, that's minus 90 degrees. Now, remember, since we have to add them, we cannot add them in this format. We need to convert each one of them to the A plus BI format. So you can do, for the first one, it's 110 cosine negative 60 degrees plus J 110 sine negative 60 degrees. For the second one, so yeah, a quick thing to keep in mind when you are writing in A plus BI, your real part, that's basically the magnitude, cosine, the angle. And for the imaginary part, that'll be the magnitude, sine, the angle. Then once we have that, you do just to combine them, you should end up with something like 55 minus J 305.26. And then you would want to convert this back to a phasor if you want to write it in the same format. So to do that, you first need a magnitude or the radius. You do 55 squared plus 305.26 squared. That gives you the radius or the magnitude. Then you want to find the angle. And as always, if you're using octant, you gotta be really careful with the angles, especially if they are negative, because your calculator might not say the right one. And you can always add or subtract 180. And a good way to check your angle, just plot out which quadrant it would be. So if you have a positive x value and a negative y value, you're going to be somewhere over here, right? So just be sure that whatever angle you get, it matches with this. And you can maybe find a positive angle, like just ignore the negative, plug this into your calculator, and then just make that angle negative. That's one option, but just be sure you check which angle you're in. So once you do that, you get 310.18, negative 79.79 degrees, and write it back in original format. We are using cosine, same frequency, and then we use the angle. So be sure to keep practicing this. You'll see it a lot. Just get comfortable with it.
Alrighty, the next concept that you will 100% see on the exam is finding the equivalent resistance, capacitors, and inductors. Um, so for this question, you got to determine where the nodes are first. So we know there's a node here, there's a node here, there's going to be a node here. So we'll start there. So we will find the equivalent resistance of 3 and 5. We can see that they share two nodes, so they are in parallel. And the formula for parallel is just going to be 1 over R1 plus 1 over R2 plus dot 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 1 over Rn. And then you find the inverse of it. Okay, so let's start with R3 and R5. So we have 1 over R3, R3 plus 1 over R5. And then we're going to invert it. And then that will give you R3, 5. And then we have 1 over 3,800 ohms plus 1 over 9,400 ohms. And then we're going to invert that, and we should get 2706.06 ohms. And that's going to be R35. Next, we will do the same thing for R4 and 6. They are also in parallel because they share two nodes. So we'll do 1 over R4 plus 1 over R6. We're going to invert it, and then that will give you R4 and 6. Let's move that there. Okay. So we have 1 over R4 is 34. Wait, R4 is 31, sorry. Yeah. R1, 3100 plus 1 over R6 is also 3100. So we're going to invert it, and then that'll give you R46. So then R46 equals 1550. Oh, that is not the ohm symbol. Ohms. All right, so now we should have something that looks like this. This is going to be R2, R1, and then we have R3, 5, and R4, 6. Next thing we will do is combine R3, 5, 4, 6, which are in series because they share one node, and R1 and 2 also share one node. So we'll combine both of them in series. We'll start with R3, 5, 6, and R3, 5, 4, 6, whatever. So that would be, all right. So that would give us, hold on, so we have 1550, 1550 ohms plus 2706.06 ohms. And that will give us that is not enough. R3, 4, 5, 6. And that should equal 4256.06 ohms. And then R1 plus R2 will give you R12. R1 is 29, that's 2900, plus R2, 8100, and that will give us 0 plus 8100. That will give us 1000 ohms. Okay, so now we should have something that looks like this. And then another one that looks like this. And this is just R3, 4, 5, 6. This is R1, 2. They're in parallel, so we can combine them. And then that will give us our resistance equivalent. So we get Req equals 1 over R12 plus 1 over R3, 4, 5, 6. And then we're going to invert it because they are parallel because they share two nodes. Req equals 1 over R12 is 11000 ohms plus 1 over 425606 ohms. And then Req will equal 3069 ohms. Make sure you guys know this because this will 100% show up on the exam, and it is something important that you guys need to know for the exam. But yeah, just make sure you know your formulas for fault solving, the resistors in equivalent, resistors in series and resistors in parallel, and you should be able to do it. Just trying to make up space here. All right, so our next problem we have is finding the equivalent capacitance. Capacitors are the opposite of resistance. So to find the series, find the capacitors in series, you'll do 1 over C1. So you'll do 1 over C1 plus 1 over C2, and then you'll invert it. And then for finding them in parallel, you can just do C1 plus C2 plus Cn. Okay. Now let's just erase that so we can save up some space. All right. So for this problem, we'll start right here. So we have two nodes here between the 9 nanofarad and the 5 nanofarad capacitors. They are in parallel. So you can just combine them by doing 9 plus 5, which equals 14 nanofarads. Then we would have something that looks like this. Oh, these are not resistors. Okay. And like that. Okay, and then this is just going to be, we can call this C1, C2, C3, and this is going to be C4. So this is going to be C1, 2, this is C3, and then this is C4. Alrighty. Now we can combine these two, C1 and 2 and C3 in series because they share one node. And then that would be 1 over 14 plus 1 over C3 is, oh, C3 is 3, sorry. And then we can invert it, which would equal 5. Okay. It would be 1 over 14 plus 1 over 3. And then that you can invert it, so it would equal 2.47 nanofarads. Alrighty, so now we have our source, our voltage source, and we have one capacitor here, and we have one capacitor here. So now we will be solving for the equivalent capacitance. This is C4, this is C1, 2, 3. To combine them, they are in parallel, so you can just simply add them. So we have 2.47 plus 6, which would equal 8.47 nanofarads, which is equal to your CEQ. That is your final answer.
Okay, so now we're going to move on to DC conditions. So DC conditions basically just means that you have inductors, you have capacitors, but there's DC current instead of AC. So if you remember correctly, in DC conditions, inductors, they become short circuits, right? Because it's just a coil of wire in the end. And then capacitors, they become open circuits, right? So first, let's redraw this circuit to represent that DC condition. So once again, we have our current source supplying 16 amps, right? We still have our resistor. And this time the inductor, remember how we said it's a piece of wire now? So that's going to short it. Then we have our other resistor. So this is 6 kilo ohms. This is still 2 kilo ohms. And then the capacitor we mentioned was an open circuit like that, right? So we can just omit it from our current model. So once again, we have I2 flowing over here. Okay, so our objective is to find the current across the 2K ohm resistor. So that's current division. How do we know that? Because we have two resistors in parallel, and we know the current coming into both the branches. Okay, what about this one? Find the voltage across the capacitor. This one, so if you notice that even though we can still like technically omit this capacitor from the circuit because it's open, it's still in parallel with the 2K ohm resistor. So if we find the voltage drop across the 2K ohm resistor, we find the voltage drop across the capacitor. So that's what we're going to do. So first step, let's find the current through the 2K ohm resistor, right? And that's current division. So if you remember, your current across R2 equals your total current coming in. And then we have sum of resistors. So both the equivalent resistance, right, which is 2K ohm plus 6 kilo ohm. And then we put the resistor here that we don't want to find the current of. AKA, we're finding the 2 kilo ohm current, right? So we're going to place 6 kilo ohm over here. So it's the resistor we don't want to find the current of. And if we plug in our values, we get 16, we get 6 kilo ohm. This is 8 kilo ohm. The kilo ohms cancel. So we have 16 times 6 over 8. And that should give us 7.5 amps. So here's the first part. We found the current going through the 2K ohm resistor. I2 equals 7.5 amps. Okay. Now we need to find the voltage drop across the capacitor. So remember, the capacitor is in parallel with the resistor because they share the same starting and ending node. So if we find the voltage drop across the resistor, we find the voltage drop across the capacitor. So let's write it like this. VC equals VR 2 kilo ohm resistor, right? So this is Ohm's law, right? The voltage drop across resistor is current times resistance. So we have 7.5 amps multiplied by 2 kilo ohms. So it should give us sorry, 7.5 should give us 15,000. If I'm correct, let me double check my answers. Yes, should be 15,000. Okay. So that's DC conditions. Now let's move on to energy of capacitors and inductors. So this one is actually quite simple. There's only two formulas to remember. So the energy in a capacitor is given by this equation. 1/2 CV squared, right? So usually you'd be given a voltage value, but now what we're saying is voltage is a function of time. So now we can just say V of t squared. Okay, so now we need to find it at specific times. So at t equals 3. So once again, we'll just start plugging in our equation. 1/2. Our capacitance is 4 microfarads. So that's 4 times 10 to the negative 6. And then our voltage. So we'll take time equals 3 and we plug it into this function. So for t equals 3, what we return is just t. So we'd just say 3 squared. For 8, right? So now let's do 8. For 8, once again, we'll plug in the same equation. 1/2. This is our capacitance now, 4 times 10 to the negative 6. And now it's a little bit different because if you plug in 8, we see that we would use this part instead of this part, right? Because it's saying the piecewise function is saying when your time is between 5 and 10, use this function. So that's what we're going to do. So now instead, what we'll do is we'll plug in t over 2 plus 2.5 squared. Remember, our t value is 8. So we end up that our final energy in our capacitor is 18 microjoules. And let's plug in our values for the next one. So 1/2, 4 times 10 to the negative 6, 8 over 2 plus 2.5 squared. So that's 8.45 times 10 to the negative 5, aka 84.5 times 10 to the negative 6. And remember, the 10 to the negative 6 is the same thing as microjoules. So this is 84.5 microjoules. And let me just double check my first answer. 1/2 times 4 times 10 to the negative 6. And then we get 3 squared. Yeah, okay. Now we'll move on to energies across inductors. So it's a similar equation. In fact, it's very close. So for capacitor, it was 1/2, sorry, energy across capacitor is 1/2 C V squared. For inductor, it's just 1/2 inductance and then the current squared. So you're only swapping two variables, but the form is still the same. So, okay, once again, we're given the current through an inductor as a piecewise function, and we need to evaluate the energy across the inductor at 3 different times. So let's first start with the top one. So at t equals 0, what we're saying is, okay, so for t equals 0, we'll first write out, I'll write it over here. T equals 0. What does that mean? So if we plug in our inductance equations, or sorry, energy across inductor equation, we get 1/2 our inductance, which is 8 Henry. So that's 8. And then once again, we have to return to this piecewise function to determine what value we're supposed to use of this. So for t equals 0, we're supposed to use this middle one because it says t is greater than or equal to 0. So what we return is 2 times our t value. So 2 times 0. And we don't actually have to evaluate this because this is multiplied by 0 over here. So it just comes out to 0. Okay, now let's do t equals 2. Once again, let's start with our equation. 1/2, this is our inductance. And then now let's look at this piecewise function to determine which part we need to use. So for t equal 2, once again, we'd use the same part because this is where t is defined for. And what we're saying is we need to return double the t value. That's our current that's going through it. So we need to return 2 times our t value. Our t is also 2. And then we square it. So this turns out to 8 over 2 times 4 squared. And let me just check. 8 over 2 times 4 squared. That should be 64 joules. Okay, now let's do the third one. T equals 15. So once again, we need to start with the equation. So 1/2 times 8, which is our inductance. And then for our current, we need to consult that piecewise function again. So t, okay, so we have t equals 15. So we'd use this one because this one is defined for when t is greater than 5, greater than or equal to 5. So this one says that no matter what t value it is above 5, you return 10. So that's all we'll do. We'll just multiply by 10 and then we'll square it. So that should be 4 times 100, which is 400 joules. And that is how you solve that question. Okay.
All right, so this is the end of the problems we are doing for the review. So we covered as probably like most of the questions that usually shows up on exams. If you all want more practice, please go to the YouTube channel, search up IEEE UTD. You'll see exam reviews from the past few years. They pretty much cover almost any type of problem you'll see. And for the most part, if you go to your homework problems, your exam is going to be pretty similar. So just go to your homework problems. Be sure you know how to do phasors, voltage division. Yeah, just know the basics and good luck on the exam.